Drop a spoonful of sugar into a cup of hot tea, give it a stir, and watch it vanish. Light an incense stick in the corner of a room, and minutes later, the scent fills the opposite side of the house. To the naked eye, the physical world looks solid and continuous. A glass of water or a wooden desk appears to be one unbroken material. These transformations indicate that the world we see is governed by a microscopic reality that plays by an entirely different set of rules. Thousands of years ago, early Greek thinkers and Indian philosophers, like Acharya Kanada, suspected this, proposing that matter was made of unimaginably tiny, indivisible units. Modern science confirms that everything around us, with mass and volume, is composed of microscopic particles called atoms and molecules. When sugar dissolves, it doesn't cease to exist. The solid crystals simply break apart into individual molecules and mix with the water. Those water molecules have microscopic empty gaps between them, called interparticle spaces. The sugar molecules slide right into these voids. The ability of one substance to hide inside another illustrates that matter is made of discrete particles separated by empty space. The primary difference between a rock, water, and air is how their particles are arranged and the strength of the attractive forces holding them together. In a solid, the particles are packed tightly together, held into a rigid structure by very strong interparticle forces. These particles are never completely still. Even in a block of iron, they constantly vibrate in their fixed positions, held too tightly to break free. In a liquid, those attractive forces weaken. The particles stay close, but they have enough freedom to slide and flow past each other, allowing the substance to take the shape of its container. In a gas, those interparticle forces drop to almost zero. The particles move rapidly in all directions, creating massive empty spaces between them. The rigidity of a desk, the flow of a river, and squeezing a balloon are all direct results of this invisible spacing and the attractive forces between particles. We can manipulate how these particles behave by adding thermal heat, which directly increases their kinetic energy, or their energy of movement. When you heat a solid, its particles vibrate faster and faster. Eventually, the movement becomes so intense that they break their rigid bonds. This is the melting point, where a solid becomes a liquid. Continued heating makes the liquid particles move fast enough to completely escape their bonds and burst into the air as a gas, the boiling point. During these transitions, the temperature remains constant. This is due to latent heat, hidden energy used entirely to break the attractive forces between the particles. A pressure cooker uses this principle. Increasing the pressure forces particles closer together, making it harder for them to escape as a gas, which raises the boiling point and cooks food faster. Heat is essentially a tool to manipulate interparticular forces, allowing us to morph matter from one physical state to another. Consider how the scent of perfume or incense travels across a seemingly still room. This spreading is called diffusion, the spontaneous movement of particles from an area of high concentration to an area of low concentration. Perfume particles burst out of a bottle and constantly collide with moving air molecules, scattering chaotically in every direction. Because gases have huge interparticular spaces and high kinetic energy, this chain reaction of collisions happens incredibly fast. Fragrance spreads through the physical collisions of invisible matter, happening at high speeds right in front of us. This kinetic energy is the exact same force at work when wet clothes dry on a hot day. Even below the boiling point, ambient heat gives surface water molecules enough kinetic energy to overcome their attractive forces and escape into the air. The ground we walk on, the water we drink, and the air we breathe are all dictated by this continuous, invisible dance of particles. Once we understand the microscopic rules of spacing, attraction, and energy, the everyday world reveals itself as predictable, beautiful science.